Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech. And this week we'll be going through Bitcoin Optech newsletter number 301, published on 8th of May 2024. And as every week, let me first go through the preface of the letter so that we get an idea of what's in store for us. This week's newsletter describes an idea for securing transactions with Lamport signatures without requiring any consensus changes. Also included are our regular sections with the summary of a Bitcoin Core PR review club, announcements of new releases and release candidates, and descriptions of changes to popular Bitcoin infrastructure software. Okay. We have two news articles. Okay. And I think we have only one news article. The other is a Core PR review club summary. So we have only one news article. I'll go through it. It's pretty long. I'll read through it first without pausing, and then we can try and bifurcate it and see what we can make of it. So it goes: consensus enforce Lamport signatures on top of ECDSA signatures. Ethan Haleman posted to the Bitcoin Dev mailing list a method for requiring that a transaction be signed by a Lamport signature in order to be valid. This can make spends of P2SH and P2WSH outputs quantum resistant, and according to Andrew Polstra, makes it so that size limits are now the only reason that Bitcoin doesn't have covenants. We'll summarize the protocol below, but to keep our description simple and clear, we will omit several security warnings, so please do not implement anything based on the summary. Lamport public keys consist of two lists of hash digests. Lamport signatures consist of the pre-images for selected hashes. A program shared between the signer and the validator interprets which pre-images are revealed as instructions. For example, Bob wants to verify that Alice signed a number between 0 and 31 in binary 5 zeros to 5 ones. Alice creates a Lamport private key from two lists of random numbers. Okay, so this is the private key. Okay, two lists of random numbers. This is the first list on top, which is named private zeros, and then the second list, which is private ones. So this is the private key basically. She hashes each of those private numbers to create her Lamport public key. Okay, so she hashes the random numbers, which is the private key, to get the public key. As you can see, private zeros, the first element hash is the public key. Okay, so each number is hashed and the corresponding output of the hash is the public key. So you hash the private key to get the public key. She gives Bob her public key. Later, she wants to verifiably communicate the number 21 to him. She sends the following pre-images. Okay, so this is if she wants to communicate a message, right? In Bitcoin, when we say that there's a digital signature, that digital signature signs something. In Bitcoin, generally, that's the transaction. Okay, now that message could be anything. Let's say that you want to sign 21. Okay, you want to convey this message. 21 is the message that you want to sign. This is how you will convey it. Okay, like 0, 1, private ones 0, private zeros 1, private ones 2, private zeros 3, private ones 4. Okay, so it means that you go to private ones and you take the 0th element, okay, here, which is 0, and then you go to private zeros, which is 1. Okay, so it's 0 1 0 1 0. Okay, that's how it is. When you see ones, that's 1. When you see zeros, that's 0. Ones, that's 1. Zeros, that's 0. Ones, that's 1. Okay, so 1 0 1 0 1. That's 21 in binary, right? 1 0 1 0 1 is 21, because this is 1 and this is 4 and this is 16, right? 1 2 4 8 16. So 1 plus 4 is 5 plus 16 is 21. So this is how you convey 21 in binary. Okay, and this is how you share the digital signature for it as far as the Lamport signatures are concerned. Okay, so 1 0 1 0 1. Okay, in binary, that's 1 0 1 0 1. Bob verifies each of the pre-images match the public keys he previously received, showing him that only Alice, with her knowledge of the pre-images, could have generated the message 21. For ECDSA signatures, Bitcoin uses the DER encoding standard, which omits leading zeros, bytes, from the signatures to components. For random values, 0 byte will occur 1 out of 256 time of the time. So Bitcoin signatures naturally vary in size. This variation is exacerbated by the leading byte, or for R values being a 0 half the time, see low R grinding. But in theory, the variation can be reduced to a transaction being 1 byte smaller, that is 1 by 256 the time. Even if a fast quantum computer allows an attacker to create signatures without prior knowledge of a private key, DER encoded ECDSA signatures will still vary in length and will still need to commit to the transactions that contain them, and that transaction will still need to include any additional data necessary to make it valid, such as hash preimages. This allows the P2SH redeem script to contain an ECDSA signature, check that will commit to the transaction, and a Lamport signature that commits to the actual size of the ECDSA signature. For example, this is the script. Okay, I'll just pause for a few seconds instead of reading the entire script. So I'll give you all time to just read the script yourselves. Okay, take 5 seconds and go through the script 5 or 10 seconds, because reading it is going to be too cumbersome. Okay, to satisfy this script fragment, the spender provides an ECDSA signature. The signature is duplicated and validated. The script fails if it's not a valid signature. In a post-quantum world, an attacker may be able to pass this test, allowing validation to continue. The size of the duplicate signature is measured. If it's equal to size bytes, the spender must reveal the preimage for digest X. The size can be set to 1 byte smaller than the common case, which naturally happens once every 256 signatures. Otherwise, in the common case or with a size inflated signature, the spender must reveal the pre-image for digest Y. If a valid pre-image for the actual signature size isn't revealed, the script fails. Now, even if ECDSA is completely broken, an attacker can't spend the bitcoins unless they also know the Lamport private key. By itself, this isn't very exciting. P2SH and P2WSH already have this fundamental property when their script pre-images are kept secret. However, after the Lamport signature is published, an attacker who wants to reuse it with a forged ECDSA signature will have to ensure the ECDSA signature is the same length as the original ECDSA signature. This may require the attacker to grind the signature, performing extra operations that an honest user won't need to perform. The amount of grinding an attacker would need to perform can be increased exponentially by including additional pairs of ECDSA and Lamport signatures. Unfortunately, because ECDSA signatures only naturally vary in byte size 1 time out of every 256, the straightforward way to do this would require a very large number of signatures to be included to obtain practical security. Hillman describes a much more efficient mechanism. That mechanism still exceeds the consensus limits for P2SH, but we think it might just barely work with P2WSH's higher limits. Additionally, an individual attacker with a fast quantum computer or a sufficiently powerful classical computer could discover a short ECDSA nonce that would allow them to easily steal from anyone who didn't anticipate a nonce that short. The minimal size of a nonce is known, so the attack is avoidable. However, the private form of that nonce is not known. So anyone trying to avoid this attack would be unable to spend their own bitcoins until a fast quantum computer was invented. This Lamport signature verification is practically similar to the proposed Optech from stack opcodes. In both cases, the data to be verified, a public key and a signature are placed on the stack, and an operation only succeeds if the signature both corresponds to the public key and commits to the data on the stack. Andrew Polstra described how this can be combined with BitVM style operations to create a covenant, although he warns that would almost certainly violate at least one consensus size limit. So yeah, we read through this Mammoth News article. Like I personally had heard this term Lamport signatures. I had no idea what they do. Okay, so I had to dig into what Lamport signatures are. Okay, and this proposal is still at very trivial stages. I mean, it's just a brain child of Ethan Hillman. Okay, so there was not a lot available on the internet for us to research on, because it's a proposal that he came up with and he shared for the first time. But still, we'll go through it and we'll see what we can make of it. So firstly, I feel in order to even try and understand what this proposal is trying to achieve, we need to know Lamport signatures. So let's first familiarize ourselves with what Lamport signatures are. I will go to where my notes are. Okay, yeah, let's just try and understand what Lamport signatures are. The font is good, readable.
Can you zoom in a little bit?
Increase it one or two more size. Yeah, this is better.
Okay. So in cryptography, A Lamport signature is a method for constructing a digital signature, and typically it involves the use of a cryptographic hash function. Okay, so the primary difference between the ECDSA signature and the Lamport signature is that in ECDSA signature we make use of uh, scalar multiplication, right? Make use of scalar multiplication, but in Lamport signature we make use of cryptographic hash functions. And this process can be explained in 3 steps. This is common to both ECDSA and Lamport signatures. Key generation. So you generate a pair of keys, a private key and the corresponding public key. That's step 1. Signature generation. Then you generate a signature and sign a message using that signature. From the private key, you generate a signature and then you sign a message using that signature. Then signature verification. Then a verifier verifies that the signature is valid, meaning the signature has been produced from the private key corresponding to the public key that you have shared. And if that signature is verified, then you are in context of Bitcoin, you have the authority to spend the transaction. Okay, so how do we go about this entire process? First, we need to create a Lamport key and a corresponding public key. Okay, so first thing, key generation. Okay, so we generate a private Lamport key and we generate its corresponding public key. Now, how do we generate a private Lamport key? This is how we do it. Okay. Should I read? Would it be better to read or? Okay, I'll read it first and then we'll go to the infograph or the diagram or whatever. Okay, so first we need to create a private Lamport key, okay, and a corresponding public key. So there's nothing new. We do this in ECDSA as well. We take a private key, then we perform scalar multiplication between that private key and the generator point, and then we get a public key. Okay, so we do, I won't say the same thing, but the concept is the same, that you have a private key and you generate a corresponding public key for it. In order to create the private key, a secure random number generator is used to generate 256 pairs of random numbers. Each number consists of 256 bits. Okay. So in ECDSA signature, what do? We have just one private key, right? It is just one random number. Okay, of 256 bits, and even for the nonce we just have one number, right? But in Lamport key, what we do is we generate 256 pairs of random numbers. Okay, so total 512. So your private key comprises of 512 random numbers or 256 pairs of random numbers. So you take a random number generator, and using that random number generator, you generate 512 values, that is pair of 256 values. So this is your private key in green. Okay, so this is the first random number, the second random number, the third random number, and the 256th random number. And like I said, pair. So the corresponding first random number, second random number, third random number, and the 256th random number. So you make a pair. This is one pair. This is another pair. This is the third pair. This is the 256th pair. So you generate 512 random numbers or 256 pairs of random numbers. That is your private key. And then what do? You hash it. You put each random number through a SHA-256 algorithm, okay, to get another output of 256 bytes. So your public key is again 512 numbers. Okay, so your public key is also a pair of 256 numbers. Okay, so you take this pair, you hash it, and that's your public key. You take this pair, you hash it, and that's your public key. Okay, so 512 random values is your private key, and then you hash each random value. 512 outputs that you get is your public key. Okay, so this is your private key, this is your public key, and then message. Okay, so you take a message. Now, for instance, that message could be anything. Okay, for instance, if you want to convey 21. Okay, if you want to convey 21, if Alice wants to convey to Bob a number, that's 21. That's the message. Okay, so she'll convert it into binary first. Okay, and then what she'll do is let's assume this is 01101. Okay, let's assume this is 21. So the first byte is 0. Okay, you convert that message into binary, so the first byte is 0. Okay, so when it's 0, what she'll do is she'll take this pk1 0. Okay, so this entire row corresponds to 0 and this entire row corresponds to 1. Okay, because we're talking pairs here, so this entire list corresponds to 0 and this entire list corresponds to 1. Okay, so every time you get a 0, you will pick an element from this list, and every time you get 1, you pick an element from this list. Okay, so here it's 0. Okay, the first byte is 0, so you pick this one. Okay, pk1 0 from your private key. The next is 1, so you go here, pick from the second list, pk2 0. Okay, then again it's 1, you go here, pk2 0, then again it's 1, you go here, pk2 PK2 255. If this was 0, you pick it from this list. If it's 1, you pick from this list. If it's 0, from this list. If it's 1, from this list. 0 from this list, 1 from this list, and 0 from this list, and 1 from this list. Okay, so this is your digital signature. Okay, because it was 0, 1, 1, and then the last number was 1. Okay, I've abbreviated it for convenience. So this will be your digital signature. So half of your private key will be your digital signature. Okay, like you took this point, and then you took this point, and then you took this one, and you took this one. Okay, so you half of your private key is your digital signature. You take that digital signature. Okay, I'll just read through this. In order to create the public key, each of the 512 random numbers are hashed. This will produce another 512 numbers, each consisting of 256 bits. This is the public key. We hash the message using a 256-bit cryptographic hash function to obtain a 256-bit digest. Okay, so this is the private key. We hashed it, got the public key, and we took the message. We put the message through our hash algorithm and got a 256-byte output. That is the message. Okay. For each bit, depending on whether the bit value is 1 or 0, we will pick the corresponding number from the pair of the numbers of the private key. That is, the bit is 0, the first number is chosen, and if the bit is 1, the second number is chosen. This results in a sequence of 256 numbers, which is the signature. Okay, so if the first bit is 0, we take from here. If it's 1, we take from here. If it's 1, we take from here. If it's 1, we take from here, and this is our digital signature. Okay, so now we know what is a private key in Lamport signatures. How is it generated? What is a public key in Lamport signatures? How it is generated? What is a message in context of Lamport signatures? How it is generated? And what is a Lamport signature? Okay, we know this. So we have all the information now. Now, how do we verify that the signature is valid? Okay, so comes the third step.
Faisal, just a small doubt. Do we operate in the finite field space like we do for ECDSA, or is it just simple binary here?
I personally could not accumulate any information confining this to working in a finite space. So the assumption has to be in absence of a finite space, because I personally could not come up with any information or any article or any paper that I went through did not mention or confine it to a finite field. So I have no reason to believe it's only over a finite field, but still I can look into it later on and let you know if it's specific or confined over a finite field.
Okay, thank you.
Yeah, okay. So yeah, we know what the private key is, what the public key is, what the message is, and what the Lamport signature is. Okay, so we have all the ingredients now. How do we verify a Lamport signature? Okay, so the verifier hashes the message using the same 256-bit cryptographic hash function to obtain a 256-bit digest. Okay, the first thing the verifier does is that the verifier converts the message into the binary format. Okay, the verifier will put the message through a hash function and take the output. So the verifier has this now. This row is with the verifier message. Okay. For each bit, depending on whether the bit value is 1 or 0, verifier will pick the corresponding number from the public key. That is, if the first bit of the hash is 0, he picks the first hash in the first pair, and so on. Okay. So now what the verifier will do is, verifier will take this. Okay, the verifier will take the signal, or the verifier will take the public key. Okay, because the public key is with verifier hashes each of the numbers in the signature to obtain a 256-bit digest. Okay, if this matches the sequence of 256 numbers that Bob has previously picked out, the signature is valid. Okay, so the verifier has the signature. What the verifier will do is verifier will hash the signature. Okay, now here remember this is 0. So verifier will hash this number, okay, this part of the signature, and check whether it matches with this. Okay, because how did we get this PBK1? PBK1 is public key, right? We hash this PK1 and we got this PBK1. Okay, so what the verifier will do is verifier will hash this PK1 that is with him, and if this hash matches with PBK1, then the signature is valid. I mean, he'll do with all of that. He'll take this PK21 and he'll hash it and compare it with this PBK21. He'll take PK22 and hash it and compare it with PBK22. It will take PK2 255, hash it and compare it with PBK2 255. So after hashing the entire signature, if it matches the corresponding public key values that have been shared with the verifier is certain that the transaction is now valid. Okay, so this is how we generate Lamport keys. This is how we generate Lamport private and public keys. This is how we generate a message or convert a message into a binary format. And this is how Lamport signatures are generated, and this is how we verify a Lamport signature. Okay, and like one thing to notice is that contrary to ECDSA's reliance on number theoretic assumptions, vulnerable to quantum computing, Lamport signatures derive their security from the difficulty of inverting hash functions. So Lamport signatures rely on hash functions, unlike ECDSA signatures that rely on scalar multiplication or what we refer to as point addition, which remains robust against quantum attacks. Okay, so this is what Lamport signatures are. Once we understand what Lamport signatures are, we'll be able to better understand, or we can try and understand this proposal in a more comprehensive manner. So, any specific questions about Lamport signature, or the broad overview of Lamport signatures is understood?
Yeah, so one question I had was, if you are revealing parts of your private key as the signature, right? So that means you'll not be able to keep repeating the same private key. I mean, repeatedly keep using the same private key to generate signatures, I guess.
Yes, that's correct.
Okay.
Because you have to reveal half of your private key every time you're using it to sign any message. So yeah, if you are revealing your private key again and again and again, so yeah, that's a high possibility. So yeah, that's ruled out. Correct.
Faisal, in ECDSA, there is this discrete log problem. Because of that, you cannot back calculate your private key. What sort of mechanism is there in Lamport signature?
You will have to break SHA-256 algorithm, or any algorithm, for instance, that you use. The example that we used, or the example that the author has given is SHA-256. So you will have to break SHA-256. And there's something else as well, which we'll talk about. Like, but basically, you'll have to break SHA-256.
One question on, is this already used in some places, maybe other cryptocurrencies or some other cryptographic tool? Or is this a completely new thing?
No, it's Lamport signatures definitely aren't a new thing. Their incorporation into Bitcoin, how they can be used in Bitcoin, is a proposal that is new. But Lamport signatures definitely are not new. I've heard this terminology on various occasions. Lamport signatures have been there, but like how can we accommodate them in Bitcoin? This proposal is very new. Okay, so Lamport signatures have been there. Okay, so now let's try and understand how the author proposes that Lamport signatures can be used in context with Bitcoin. Okay, so now basically what happens is to basically create a digital signature, without the knowledge of a public key. Okay, what you have to do is you have to solve the DLP, which we call the discrete log problem. Okay, so now let's assume that the computers become very advanced and they are able of cracking the DLP. Okay, so the quantum computers are capable of generating digital signatures without the knowledge of private keys to sign a transaction. So what do we do in such a situation? We add ECDSA signatures along with Lamport signatures. Now, what role do Lamport signatures play here? Okay, firstly, as far as Bitcoin is concerned, currently the signature checking mechanism that we have only checks the signatures for the transaction itself. Okay, when we say we're signing something, then there needs to be a message that we are signing, right? But Bitcoin currently, the opcodes that are used for signature verification can only verify digital signatures where the message is the transaction itself. You cannot sign arbitrary data and put it on the script and verify it using Optech-sig or Optech-sig verify or Optech multisig. Okay, it's only the transaction that can be used as a message. Okay, but Lamport signature, I mean, this proposal introduces Lamport signature with an intention of signing arbitrary data. Lamport signatures will not sign the transaction itself. Then what will Lamport signatures sign? Lamport signatures will sign the size of the ECDSA signature. Okay, so ECDSA signatures are normally 32 bytes in length. Okay, but what happens is that we refer to this DER encoding standard, right? Distinguished encoding rules. We follow this standard. Now, according to this standard, if an ECDSA signature has zeros at the start, okay, if it has zeros at the start, those zeros get truncated. Okay, and I'll show you an example so we can better understand what I'm talking about, how the zeros get truncated. So if you have a 32 byte ECDSA signature where you have 2 zeros at the start, or 3 zeros at the start, or 4 zeros at the start, those zeros will get truncated, and after truncating, whatever remains will be considered as the size of the transaction. So let's assume this is a digital signature. Okay, and the signature just happens to be that there is 00000. The first 11 bytes are 0. Okay, so those 11 bytes will get truncated. This is how DER encoding standard works. Okay, and so 88 bits or what you can say 11 bytes will get truncated. So instead of 32 bytes, now your signature is only of 21 bytes. Okay, so what we'll do is when you create an ECDSA signature and you see that the signature is of 21 bytes, okay? So the message that I'm talking about that we are going to sign 21 is the size of the ECDSA signature, right? So the person who is trying to spend the transaction will use the size of the ECDSA signature as the message and use the Lamport signature to sign this message, okay? And then once that is done, they will convey it this way, okay? This way, like we talked about it, like 10101 in binary, okay? So this is the message, okay? Now what to crack this, or even if you are able to crack the ECDSA signature, Lamport signature is still there, which has signed the message, okay, which has signed the message. So you also need either the Lamport private key, that is all these 512 random numbers. You either need all these 512 random numbers, or the second option is, if without the knowledge of the private key you want to generate a valid digital signature, you have to ensure that that digital signature is of the same size, okay? So I create a transaction, okay, and I send it to someone, and my digital signature is of 21 bytes, for instance. So I will convert those 21 bytes, that size of the digital signature, into binary format, okay, and sign this binary format, this message, using the Lamport key, okay. So either you know my private key entirely, or the second mechanism, without the knowledge of my private key, if you want to create a digital signature which can validate the transaction, you have to ensure that that digital signature also has to be of 21 bytes. Okay, so now the hacker is not only in need of creating a digital signature, the hacker is also in need of creating a digital signature which should have the exact number of zeros that I have at the start of my signature. Okay, so if somebody wants to hack, like if somebody wants to create an ECDSA signature without the knowledge of my private key, okay, as long as that digital signature is able to validate the transaction, the size is irrelevant. But now we're adding another catch, okay? Even if you somehow manage to find a digital signature for the message that I've signed using Lamport signatures, you have to ensure that whether it's brute forcing or whatever, you have to ensure that your digital signature should have the exact number of zeros at the beginning that my digital signature has, and only then will you be able to spend the transaction. So this kind of increases the work of the hacker, okay, that instead of just finding a digital signature that satisfies my message, or that is able to unlock my message, they have to find a digital signature without the knowledge of my Lamport key that is exactly the same in size as my ECDSA signature. And this is how the script works, okay? So instead of using
if I can ask, like, where does the number 21 come from? The risk in Lamport signatures, as I understand, that every time you sign, you reveal, one of the two private keys at that 0th, 1st, 2nd location. So it's easier for you to, like, if you have a lot of signature information, it's easier for you to copy a potential signature which can be signed. Now that I understand, but in this case, you are saying even if you were to come up with the same kind of signature, you need to fulfill another condition, that it has to have 21 zeros at the start. Like, why 21 zeros at the start? I could not understand that.
Okay, so as far as revealing a private key is concerned, I mean, even Basanta had, he brought up the same point, and it is like, yes, you don't use your private key, even in general situations, whether it's ECDSA or Lamport, like it's a practice that you don't use your private key to sign multiple transactions, okay? Because as far as ECDSA is concerned, if you are using a nonce generator which is not safe enough, which does not generate adequate entropy, and your random number generator generates the same nonce twice, then you're gone. Okay, so if you sign two different transactions or two different messages, I'm talking about ECDSA now. In ECDSA, if you sign two different transactions with the same private key and the same nonce, then your private key will be revealed. So you should never use your private key again, whether it's ECDSA or whether it's Lamport. This, I believe, is common to cryptography, that you should not use your same private key to sign multiple messages. Okay, so that is ruled out as fair as people who practice safety measures, who take safety measures into account. We will not reuse our public key. So that is hopefully ruled out of the equation. Now, where did this 21 come from? in ECDSA signature, okay, like the ECDSA signatures need to combine with these protocols, DER encoding standard, okay, distinguished encoding rules, okay. Now, what do they say? They say that when you generate an ECDSA signature, which is a 32 bytes, if if the signature starts with zeros, okay, zeros, those zeros will be truncated. Okay, they will not be taken into consideration. Okay, so let's say this is your digital signature. Okay, and it starts with 11 zeros, which is 11 byte. Okay, like one digit is 1 byte. Okay, so with 11 bytes. So what will happen is that an ECDSA signature I told you is of 32 bytes, but because the first 11 bytes are zeros, we will truncate those first 11 bytes, and only this much will be considered as the signature. So instead of 32 bytes, we have 11 bytes. This is just an example. It could be anything. If you have two zeros, then 32 minus 2 is 29. If you have four zeros, then 32 minus 4 is 28. But here in our example, we have 11 zeros. So 32 minus 11 is 21. So we're just using this 21 as an example. It could be anything. You just remove your truncate your zeros, and then you see what's the weight of the size of the signature. In our example, we've just taken an example of 21 bytes. It's not something hard coded. Okay, and this is how you convey 21 in binary. Okay, 1 0 1 0 1. Okay, so this is 1, and this is 2, and this is 4, and this is 8, and this is 16. So 1 plus 4 is 5, 5 plus 16 is 21. Okay, so this is where this 21 comes from. You got that, Saurabh?
Yeah, I got it. Thanks.
Okay. Yeah, all right. Yeah, so that is what has to be done, and the script as a whole is like this, okay? Because just now I mentioned that opcheck sig verify, check multisig, all the opcodes that verify digital signatures in Bitcoin are not capable of verifying arbitrary data. Okay, there's another. They can only verify transactions. Only if you sign transactions can they verify it. There's another signature verification opcode that is being proposed, which is opcheck sig from stack, and a lot of people talk about it when they talk about covenants, and it is proposed that this will be able to verify arbitrary data. The templates, as we say, opctv check template verify, it will be used to verify the template of the transaction in covenants. So, but that also is being proposed. It's not a part of Bitcoin right now. So what we'll do is we use op size, okay, and we'll put the size of the transaction, which is 21. Okay, so then you need to present the digest which is of the same size. Okay, so what we do is we know the size is equal to size bytes, op shadow 56 digest x op check equal verify, and op shadow 56 digest y op check equal verify. So you don't exactly know what size your digital signature is going to be, so you can't create a script to verify whether the signature is a 1 byte or 2 byte or 3 byte or 4 byte or 10 15 20 25 till 32. You can't create 32 conditions. So what you do is you just stipulate a size, okay, and you'll check if the script or if the signature is of the same size, or else if it's less than it or it's greater than it. So you take any value, let's say 31. Okay, so you check if the signature is of 31 bytes. Okay, if it's not of 31 bytes, and whether it's of less bytes or whether it's of more bytes. That's how you check it, and that's how you use the script into consideration. Okay, now we also have this mechanism in P2SH. Okay, like in P2SH and P2WSH, what do? We hash the scripts, right? But when you want to redeem the transaction, you have to present the base script, right? You have to present the base script. So that is what we're doing. Like when you want to spend the transaction, you will have to produce your entire private key. But one layer of added security that we're adding is that we are committing to the size of the ECDSS signature. Okay, so along, even if somebody manages to find a valid digital signature, that digital signature should have exactly the same number of zeros and should be exactly the same in size as the digital signature which was used by the person, the rightful owner of the transaction. Okay, so this is how it is claimed. A broader understanding of what I could garner, what Lamport signatures are, how they are being proposed or to be incorporated in Bitcoin, how even if ECDSS signatures are cracked, Lamport signatures can add an additional layer of security, because now you don't only need to generate a digital signature which is valid, you also need to generate a digital signature which is of exactly the same size which was generated when the transaction was created by the actual spender. And also you can add multiple signatures. Okay, so like instead of one ECDSS signature, you can add 2, 3, 4 different ECDSS signatures, and you can add 2, 3, 4 different Lamport signatures, so that you keep on exponentially increasing the work that the hacker has to do. Even if he has a quantum computer, you make your script quantum resistant. That is as a whole what the proposal was and what I could garner. If any questions or anything anybody would like to share pertaining what we've covered so far, please go ahead and do so.
So I just shared a resource on Lamport signatures in the chat. There's a attached video. It talks about all kinds of signatures, but like very useful if someone wants to, have a look at like what Lamport signatures are, why have they not been chosen on Bitcoin, like to begin with, and ECDSA was chosen, and all of those things.
Right. Yeah. I'll definitely check it out later post the session. Yeah. Okay. So yeah, this is all we had for the news article. We can move on to our monthly core PR review club. Okay. So in this monthly section, we summarize the recent Bitcoin Core PR review club meeting, highlighting some of the important questions and answers. Click on the question below to see a summary of the answer from the meeting. Index TxOrphanage by WTXID allows entries with same TxID. Is a PR by Gloria Zhao, GitHub Glozao, that allows multiple transactions with the same TxID to exist in TxOrphanage and at the same time by indexing them on WTXID instead of TxID. This PR makes the opportunistic one parent, one child, 1P1C package acceptance introduced in Bitcoin Core PR number 28970 more robust. Okay. So let's open this. Yeah. Let's just read through this and then we'll try and discuss this. So an orphan transaction is a transaction with missing inputs. The P2P code uses the TxOrphanage to store orphan transactions to be reconsidered later if or when its parent transactions are submitted to mempool. So what is an orphan transaction? An orphan transaction is a transaction whose parents are missing. So if your node sees a transaction such that the parent or parents of that transaction is missing, that transaction will be considered by your node as an orphan transaction, and there's an orphanage. Okay, there's a class by the name of TxOrphanage where those transactions are put. So they are saved in memory. You put them in memory and you wait till you spot their parents, okay? Because you cannot spend a transaction until and unless the parents of the transaction are confirmed, right? So when you see an orphan transaction such that the parents are missing, you before seeing the parent, you see the child. So you take the child and you consider that child as an orphan child and you put it in a place in your memory, which is known as orphanage, and you wait till you spot its parents. There are two ways this can happen, okay? Process orphan TX, which is called at the start of each process messages, pops orphans from a work set that is updated whenever a parent transaction is accepted to mempool. When a low fee rate parent with its child in the orphanage to be submitted together as package, this happens in two locations: when a transaction fails for being low fee rate, when a low fee rate parent is downloaded again, this opportunistic one parent, one child package submission logic was added in PR number 28970. So what could be the reason for a transaction to enter the orphanage? Okay, and how does this process happen? Okay, so this process messages, it's a function. Okay, it's a function in Bitcoin Core. This process message is triggered every time your node sees a new message, right? What a node's doing on the P2P network, they are constantly gossiping, right? So every piece of information that you receive is a message. It could be a transaction, it could be a block, it could be a request from some other block asking you for some data. It could be an RPC command that some block or some peer has triggered. Okay, so all of these pieces of information that are shared to and fro are messages. Every time it receives a message, it triggers this function process message. Now, what does this process message do? Okay, this process message further triggers a process orphan transaction. Okay, process orphan transaction. What does this process orphan transaction do? It looks into the orphanage to see whether there is an orphan transaction which can be pulled out of the orphanage. Okay, the reason due to which it was in the orphanage, if it has ceased to exist, then that transaction will be put out of the orphanage. Like for instance, if the parent is found, okay, the parent is found, then that transaction will be put out of the orphanage, or if the parent is low fee rate, okay, then the parent and the child will be put together and both of them will be relate together. And this is what we call 1P, 1C, or we call it as V3 relay transactions, regarding which we've discussed in detail in the VCD sessions, okay. And often can be removed in a few different ways when it is successfully submitted to mempool, if it is confirmed or conflicted in a block, if the peer that sent this orphan disconnects after it has been in the orphanage for more than 20 minutes, if it is randomly selected for eviction when the orphanage reaches maximum capacity, if it is found to be invalid for some reason other than missing inputs. For example, a transaction may be missing two parents and we have only accepted one of them to the mempool so far. In that case, we keep the orphan and will reconsider it again after the second parent is submitted. Different transactions can have the same TxID but different witnesses, that is different WTXIDs. For example, a same TxID different witness transaction can have an invalid signature and thus be invalid, or a larger witness but same fee and thus lower fee rate. In previous review clubs, we have covered same TxID different witness transactions in relation to transaction broadcasts and mempool replacements. We also covered adding TxID versus WTXID type safely to TxOrphanage in a previous club. Prior to this PR, the TxOrphanage is indexed by TxID, and when considering a new transaction in add-tx, immediately fails if the new transaction's TxID matches that of an existing entry. TxOrphanage have tx takes a gen TxID to query the data structure by either TxID or WTXID. Have tx is primarily called by already have tx, which also accepts a gen TxID. Okay. So up till now, what was happening is that when a transaction goes into the orphanage, it was being referred to, it was being indexed using a TxID, right? Because a transaction needs a TxID, a transaction ID on the network for you to access it, right? It's an identifier. It's the ID of the transaction. Now, let's say that there is a transaction in the orphanage and another transaction with the same TxID also comes to the orphanage. Now, in this situation, what was happening is that two transactions with the same TxID cannot exist in the orphanage. Okay. And now, since we know, with SegWit, what has happened is that every transaction now has a TxID and it has a WTXID. Okay, it has a TxID and it has a WTXID. So it's possible that a transaction can have the same TxID but a different TxID. Okay. So what was happening is that because the transactions were getting indexed in the orphanage using the TxID, if a transaction by a certain TxID already exists in the orphanage, and let's say that transaction is invalid for some reason, and now the legitimate transaction or the valid transaction is trying to enter the orphanage, that valid transaction will not be allowed to enter the orphanage because the invalid transaction with the same transaction ID is already in the orphanage. And when the software is designed in such a way that when an orphan transaction has a specific TxID and it's in the orphanage, it will not allow another transaction with the same TxID to enter the orphanage. Okay, now what's being done is that transactions in the orphanage will be indexed by their WTXID. Okay, so multiple transactions having the same transaction ID can coexist in the orphanage as long as they have different WTXID, as long as they have a different witness transaction ID. Okay, so just in case there is a transaction that enters the orphanage, okay, and it has an invalid digital signature for some reason, and then another transaction with the same TxID comes and it has a valid digital signature. So in this situation, both these transactions can coexist in the orphanage. Okay, because you cannot validate whether a transaction is you cannot check whether a transaction is valid or invalid until and unless you don't have access to its parents. And the entire purpose of having an orphanage is to store transactions that don't have parents. So you cannot verify whether the digital signature is valid or invalid until and unless you don't have parents. So it's possible that a transaction enters the orphanage with an invalid digital signature. Okay, and then another transaction comes, or the same transaction comes with a valid digital signature, but because they have the same TxID, the valid one will not be allowed to enter the orphanage. But now, because we're indexing the transaction using the WTXID, okay, so two transactions or multiple transactions with the same TxID can coexist in the orphanage, and this way we do not kick out the valid or the legitimate transaction out from the orphanage. That is what this PR achieves. So we'll go into the questions and answers. Anything to share or any questions pertaining to the approach of this PR or the concept of this PR? Okay, cool. We'll go into the questions and the answers. Let me see if I can highlight them. Yeah. Why would we want to allow multiple transactions with the same TX ID to exist in the TX orphanage at the same time? What kind of situation does this prevent? By definition, the witness data of orphan transactions cannot be validated because the parent transaction is unknown. When multiple transactions with different WTX IDs of the same TX ID are received, it is thus impossible to know which version is the correct one. By allowing them to exist in parallel inside TX orphanage, an attacker is prevented from sending an incorrect mediated version that prevents further acceptance of the correct version. So this is the logic, or this is the reason behind shifting from TX IDs to WTX IDs to reference transactions in the orphanage, because it's possible that a transaction comes with an invalid digital signature, and because we cannot check whether it's valid or it's invalid, we've included this in the orphanage already, and then the transaction comes with a valid signature and we don't allow it to enter the orphanage. So now we are referencing the orphan transactions using witness TX ID. So even if two transactions have the same TX ID, we allow them into the orphanage, and then the one with the valid digital signature will get accepted as a valid transaction. What are some examples of same TX ID different witness offers? A same TX ID different witness transaction can have an invalid signature and thus be invalid, or a larger witness but same fee and thus lower fee rate. Okay, so we've covered this already. Let's consider the effects of only allowing one entry per TX ID. What happens if a malicious peer sends us a mutated version of the orphan transaction where the parent is not low fee rate? What needs to happen for us to end up accepting this child to mempool? There are multiple answers. When a mutated child is in the orphanage and a valid, not low fee rate parent is received, the parent will be accepted into the mempool and the mutated child invalidated and removed from the orphanage. So if the child is invalid and it's in the orphanage and the parent is valid, then what happens when the parent is relayed? It's only the parent that enters that gets assigned and gets selected, and the child gets kicked out of the orphanage, because now that we have the parent, we can validate whether the child has a authentic digital signature or no. Okay, and if it doesn't have it, then only the parent will be relayed further and the child will be considered invalid and will be removed from the orphanage. Let's consider the effects if we have one parent, one child, 1P, 1C package where the parent is low fee rate and must be submitted with its child. What needs to happen for us to end up accepting the correct parent plus child package to mempool? Now, since the parent is low fee rate, it will not be accepted into the mempool by itself. However, since Bitcoin Core PR number 28970, it can be opportunistically accepted as a one parent, one child package if the child is in the orphanage. If the orphan child is mutated, the parent is rejected from the mempool and the orphan removed from the orphanage. Okay, so if there is an orphan child in the orphanage which pays a high fee and there is a parent that is paying the low fee, then in this situation, if the child is valid, we couple the child with the parent, okay, and then we relate them as the package. And if the child is invalid, then obviously the child gets removed from the orphanage and the parent is also not related, because the parent is also not included in the mempool because the parent is paying a very low fee. Instead of allowing multiple transactions with the same TX ID, where we are obviously wasting some space or a version we will not accept, should we allow a transaction to replace an existing entry in the TX orphanage? What would be the requirements for replacement? It appears there is no good metric by which to judge whether a transaction should be allowed to replace an existing one. One potential avenue to explore is to replace duplicated transactions from the same peer only. So this question, what it says is that we already have an orphan transaction in the orphanage. Now, if another orphan transaction comes with the same TX ID, why not just kick out the transaction that is already in the orphanage and substitute it with the new transaction? Okay. Now, there is no solution to this problem, because any transaction that is in the orphanage, we cannot verify whether it has a valid digital signature or no, because the parents are missing. Okay, so we cannot be sure that the transaction that is already in the orphanage is the valid one and the one that's trying to enter the orphanage is an invalid one, or we cannot infer that the one which is inside the orphanage is an invalid one and the one that's trying to enter is a valid one. We have no avenue to judge that. Okay, so the only fix or the only solution is that we allow multiple orphan transactions to coexist in the orphanage having the same TX ID but having different WTX ID. One potential avenue would be to replace duplicated transactions from the same peer only. Okay, so one possible solution could be that if the same node sends you two orphan transactions, okay, with the same TxID, then you replace the second one with the first, because there is a high possibility that first the node sent a transaction which was invalid, or wants to invalidate that, or wants to replace that for some reason, and that is why it again sends the same transaction with the same TxID. So that this could be an inclination towards going to that mechanism. But as of now, the only thing we can do is allow those orphan transactions with same TxID to coexist in the orphanage. Yeah, we've covered all the questions, and hopefully the concept of this core PR review club that was done this week itself, which talks about indexing the transactions in the TxOrphanage by WTxID instead of the TxID. So, any questions, any thoughts, any comments about this PR?
None from my side.
Cool. All right. Release and release candidates. Okay, so there are two lipstick P 256K1 version 0.5.0 is the release of this library for performing Bitcoin related cryptographic operations. It speeds up key generation and signing and reduces the compile size, which we expect to benefit embedded users in particular. It also adds a function for sorting public keys. So a new version of lipstick P256K1 has been released, which has some like upgraded functions, like it speeds up key generation and signing mechanism and reduces the compile size. Okay, so it gives a more optimized usage for embedded users. I believe embedded users are users that work with limited specifications, that are using devices with limited hardware specifications, and it also adds a function for sorting public keys. LND version 0.18.0 beta RC1 is the release candidate for the next major version of this popular LN node. Okay, so there's a beta release candidate out for LND. We have notable code and documentation changes. How many? We have 3. Let's try and wind up by 9:10 so that we don't exceed more than an hour. We started at 8:05. Let's see if we can wind up by 9:05. Yeah, we'll be able to wind up by 9:05 for sure. So the first notable change is Bitcoin Core PR number 28970 and 30012. What it does is it adds support for a limited form of one parent, one child, one key, one C package relay that doesn't require any changes to the P2P protocol. Imagine Alice has a parent transaction below any of her peers BIP 133 fee filter setting, discouraging her from relaying it out of the knowledge that none of her peers will accept it. She also has a child transaction that pays enough fee rate alongside its parent for both of them to be above the fee filter. Alice and her peer perform the following process. Alice relays the child transaction to her peer. Her peer realizes it doesn't have the transaction's parents, so it puts the transaction into its orphan pool. All versions of Bitcoin Core for over a decade have had an orphan pool where they temporarily store a limited number of transactions that were received before their parents. This compensates for the fact that on a P2P network, transactions can sometimes naturally be received out of order. A few moments later, Alice relays the parent transaction to her peer. Before this merged PR, the peer would notice that the parent's fee rate was too low and refused to accept it. Now that it had evaluated the parent transaction, it would also remove the child transaction from the orphan pool. After this PR, the peer notices that it has a child for the parent in its orphan pool and evaluates aggregate fee rate of both transactions together, allowing them both into the mempool if that fee rate is above its floor, and if they're both otherwise acceptable according to the node's local policy. So this basically, I feel, is an amalgamation of a lot of things that we've covered today. This talks about V3 transaction relay policies, that which are, I believe, on struct transactions or one parent, one child package relay, and what we talked about the orphanage. Okay, so what happens if there is a transaction? Okay, assume a parent transaction that has a very low fee, that is below the dust fee. Okay, so Alice has this parent transaction that has a very low fee. Now, when Alice relays this transaction to its peers, the peers will not relay it because the transaction has a very low fee. Okay, but what the peers can do is that the peers can check the orphanage. Okay, so the peers check the orphanage and see that this parent transaction that has a very low fee and it has a very low fee, but it also has a child in the orphanage that pays a high fee. So they will take the parent transaction with the low fee and the child transaction in the orphanage with a high fee, and they will see the aggregate fee that the entire package of the child and parent are willing to pay. And if the entire package of the child and the parent are paying a fee which is above the minimum fee that the node accepts to relay the transaction, then the nodes will accept that transaction and they will relay that transaction. Okay, so this what this PR does is that it makes use of the orphanage and the package relay mechanism to package a parent transaction with low fee with a child that is in orphanage with a high fee, and calculates the fee of the entire package, and if it's above the threshold, then the entire package will be relayed and the child will be removed from the orphanage. This is what this or these two PRs achieve. The second one is Bitcoin Core PR number 28016 begins waiting for all seed nodes to be polled before polling DNS seeds. Users can configure both seed nodes and DNS seeds. A seed node is a regular Bitcoin full node. Bitcoin Core can open a TCP connection to the node, request a list of addresses for potential peers, and close the connection. A DNS seed returns IP addresses for potential peers over DNS, allowing that information to travel and be cached over across the DNS network, so the owner of the DNS seed server doesn't learn the IP address of the client requesting the information. By default, a Bitcoin Core attempts to connect to peers whose IP addresses it has already learned about. If none of those connections are successful, it polls the DNS seeds. If none of the DNS seeds are reachable, it contacts a set of hard-coded seed nodes. Users may optionally provide their own list of seed nodes to contact. Before this PR, if a user configured polling of seed nodes and kept the default configuration to also use DNS seeds, they would both be contacted in parallel, and whichever was faster would dominate the peer addresses that the node would try. Given the lower overhead of DNS and the fact that results might already be cached by a server physically near the user, DNS would usually win. After this PR, seed nodes are given preference due to the belief that a user who sets a non-default seed node option would prefer the result of that option over default result. Okay. So when a new node is bootstrapping, okay, the new node does not have any peers. So the new node, when it is bootstrapping, is in need of peers. Now, how does the new node get access to peers? There are two ways. Okay, one is by querying a seed node, and the second is by querying a DNS. Okay, now seed nodes are full nodes. Okay, they are full nodes. And these seed nodes are hard coded into the software. Okay, so you either query these seed nodes and they will share a set of IP addresses with you that you can connect with and establish a connection with them and take them as your peers. The other mechanism is that we query the DNS. Okay, we all know what a DNS is. So you query a DNS, and that DNS will share a list of IP addresses with you. Okay, and you can establish connections with the nodes having those respective IP addresses that the DNS has shared with you. Okay, so up till now, by default, it was the DNS seeds that were being connected. Okay, and until and unless you don't stipulate and you don't specify a specific seed node that you want to query, the query would always go to the DNS. Okay, and the DNS would provide you IP addresses. Even if you would stipulate a seed node, okay, if you specified a certain seed node, a trustworthy seed node, a trustworthy full node from whom you want access to IP addresses, both these processes would run in parallel. Okay, so your node would also query the seed node, and your node would also query the DNS. Okay, and whoever responds first, those IP addresses will be taken as your peers. And generally, it's the DNS that responds quickly because it has all this information stored in its cache. So if you're parallelly creating the seed node and also the DNS, what happens is that almost always the DNS will give you information beforehand. Okay. So now what this PR does is that if a user is specifying a seed node, okay, then that seed node will get preference. Okay. So first all the seed nodes that you have specified will be queried. Okay. And if all the seed nodes for some reason could not give you the relevant IP addresses, only then the query will be made to the DNS. Okay. The reason being, if a node runner is specifying a seed node, then there is a reason for it, right? The node runner trusts that seed node, and that is why it does not want to trust the DNS server. Okay. It wants to trust a specific full node. Okay. And that is why it is specifying a certain seed node from which it wants IP addresses. Okay. So what this PR does is that if a Bitcoin node runner is bootstrapping its node, okay, and it is in need of establishing connection with peers, and it is querying both the seed nodes and the DNS seeds, it is the seed nodes that will get first preference to share IP addresses with it. And only after it has queried all the seed nodes, if the need be, it will go onto the DNS. Okay, so the seed nodes now get a preference over the DNS, which was not the case earlier. So that's what this PR does, 28016. The final one, we can commence the session with this. Bitcoin Core PR number 2960 makes various improvements to warning users if their local time seems to be more than 10 minutes out of sync with the time of their connected peers. A node with a bad clock might temporarily reject valid blocks, which can lead to several potentially severe security problems. This is a follow-up to the removal of network adjusted time from consensus code seen newsletter number 288. So what happens is that if the local time of your node is more than 10 minutes out of sync with your connected peers, you will get notified that, hey, your local clock is not precise. It has a more than 10-minute lag. It's either 10 minutes behind or it's 10 minutes ahead of your peers, so that you can adjust your local clock. And we've talked about this in detail. We even covered an entire PR that was done on nuking the network adjusted time, and how the network adjusted time is now being calculated using your device's local time and not by querying your inbound peers. And we've also discussed about the time warp attack when you were talking about the great consensus soft fork, about how having invalid timestamps can lead to manipulation. So like, yeah, this puts all of that into place, and shows how critical and how important it is for your local system's clock to be in sync with your peers. So if your local system's clock is varies in comparison with your peers by more than 10 minutes, you will get notified about it, so that you can make amendments and fix your local clock. That is all we had to cover in this week's session. 3 code and documentation changes, 2 releases and release candidates, 1 PR code review club, and one news article about Lamport signatures. That's all we have for this session. If anybody has any closing comments, thoughts, or questions, feel free to go ahead and share your views.
Nothing related to the post, but I'm always amazed by Fazil, your concentration and your ability to not let us deviate anywhere from the Optech itself. So yeah, that's an amazing trait, and that's an amazing way in which you conduct Optech reading sessions.
Thank you. Thanks so much, Saurabh. Anything else? Bala, Jatin, Shriyan, Mango, anything to share? Anything other than the Optech you all want to talk? Okay.